Hello everyone, my name is Shashank, and I'm a data analyst on my journey to become a data scientist. In that journey, I'm going through the book Hands-on Machine Learning with Scikit-Learn Keras Tensorflow, which you'll see on the screen right now. In this book is considered kind of the Bible by some data scientists of machine learning, and kind of the idea behind this book is that I want to go through it, understand how these algorithms work. That way I'm not just implementing stuff I don't really understand. So right now we are on chapter 9, which is about unsupervised learning. Basically, what we've been doing so far is something called supervised learning, except for the previous chapter. The previous chapter, we actually did some unsupervised learning in the form of dimensionality reduction, but now we're going to go fully into unsupervised learning. I'm thinking I might take a break from this book after this chapter, because this book is split into two parts, part 1 and part 2. Part 1 is all these machine learning algorithms, like your basic machine learning algorithms, kind of like the fundamentals of machine learning. And chapter 2 is really about neural networks, which I've already taken my Google TensorFlow development certification, and because of that I have a decent idea of how TensorFlow works, and I personally don't use neural networks on, I don't see much of a use for them in a lot of the stuff I do on a daily basis. So maybe I'll come back to it, but I think for now, after this, we'll probably take a break from this, and maybe we'll get into some more hardcore statistics. I think that might be something more interesting, and where my skills could use a little bit of polishing. But before we get started, I'd like to take a moment to talk about my Patreon. I really love doing this for you guys. I really like making these videos and spreading the knowledge and everything. And my Patreon is one way that you can help ensure that I'm able to continue doing this for the long run. I do some consulting on the side, and then I obviously have my full-time job. And as I'm able to get more people onto Patreon, I'm able to do less and less consulting and dedicate more time to the YouTube channel. If you join the Patreon, you'll get access to all of the notes that we're going to be going over in this chapter, along with all of the notes from previous chapters as well. And we have a Discord community. There's a private messaging feature where if you want me to check your resume and stuff, I'll go ahead and look at it. So I am trying to see how I can add more value to my patrons, but more than anything, my patrons allow me to spend more and more time doing this. So thank you guys so much for your attention, and let's get on with the show. All right, so chapter 9, Dimensionality Reduction. Okay, come on. Let's move you over here. Cool. And then let's zoom in a little bit so it's easier for people to see. All right, so most applications of machine learning that we've gone through so far use supervised learning. And what is supervised learning? Practically speaking, what supervised learning means is you have an X and a Y, meaning that you're trying to fit your X, meaning all of your features, all of your columns, to your Y. Unsupervised learning, basically you're just dropping that Y. You don't have that Y anymore, and you're just telling the machine learning algorithm, hey, given this data, go find some insight for me. And that's what unsupervised learning is. Now, although a majority of machine learning applications today use supervised learning, the author makes a very interesting point that the majority of the data on Earth today is unlabeled, because obviously if you have a Y, that means you have labeled data. And because the majority of data is unlabeled, it probably makes sense that unsupervised learning has a lot of potential in the future, and there's a lot of untapped potential in unsupervised learning. So that's what we're going to be going over in this chapter. We'll be mostly focusing on k-means, k-means clustering, but we're going to go over dbScan and GMMs, Gaussian mixture models, that's it, at the end too. And the GMMs are really why this chapter took a long time to put out. There's a lot of content in this chapter, as I'm sure you can tell. You know, the notes go on for a while because this chapter was quite long. All right, so some of the most common uses of unsupervised learning include clustering, anomaly detection, and density estimation. So clustering is basically where you have a bunch of data and you want to see, okay, how do these instances cluster around each other? And we'll be going over an example that I'm going to do live in a second where we'll demonstrate this. Anomaly detection is trying to determine what's normal and where are the abnormal values. So for example, say you're trying to detect credit card fraud. Most transactions probably fall under some degree of like normal, as in like there's a cluster of them and these are like more or less normal transactions, especially at the customer level. And then anything that falls out of that is an anomaly. So for example, I have a Chase card. So Chase is a major bank in the United States. And what happens is they recently removed the necessity for you to tell them when you're leaving the country. I don't know if that has anything to do with COVID or not, but basically, normally whenever you leave the country, you have to tell your bank, oh, I'm leaving the country. That way they know that your card's not being used by some rando in some random country. But I don't have to do that anymore. I went to the UK recently, and they didn't ask me to do that at all. And I'm guessing that they're using some kind of clustering algorithm to determine, maybe even at the customer level, maybe even they have like a cluster for me after I have thousands of transactions, right? So they probably have some idea of what normal transactions are for me, and they're able to determine, okay, these are normal transactions for this person, these are abnormal transactions for this person. That being said, every time I've left when I went to India, my card was scammed almost instantly, and when I went to the UK, same thing happened. Like within like 3 days, my card was scammed. So maybe this algorithm doesn't work really well. And then finally, we have something called density estimation, and this is the process of trying to determine the probability density function. And this is something we'll go over when I start going over some statistics and stuff. So the probability density function of a random process, usually so that we can find anomalies which are located in areas of low density. Speaking of which, if you guys have any good textbooks for statistics, or like maybe a course I should go through, I think I'm going to go through like a video course. I'm a lot better at like watching videos than I am at reading, and that'll probably be the next set of videos that we do. So those are three major applications of clustering algorithms. Sorry, unsupervised learning. So clustering is similar to classification. It's basically classification if you remove the Y. So you normally have like a bunch of X features and then some Y you're trying to predict for. Just imagine you remove that Y. That's basically what we're doing when we are clustering. So we're going to use k-means, which is an efficient and quick clustering algorithm that can be used to rapidly cluster relatively sparse data sets. There are some limitations to k-means that we'll be going over in a second. So as you can see over here, basically all we're doing is, it's very simple, just from sklearn.cluster import k-means. You tell it the number of clusters you want to look for, and then instantiate your class with the method, or while also specifying the variable n clusters equals k. Y prediction equals k-means.fitPredict x. So basically it's assigning every k-means, it's assigning every instance, so every row of your data, some group from 0 through 4, meaning 5 values, because we told it to cluster into 5 different groups. And then you can see where the cluster centers are, and then you can go ahead and predict it for an X test if you have it. So here's kind of what's happening over here. So in this example, there's only 2 dimensions of data. There's x1, there's x2. And you'll see k-means basically determine that, okay, there are 1, 2, 3, 4, 5 basic centers of your data. It's a really simple algorithm. Basically what it does is it goes ahead and it finds a center. So you have 5 clusters, right? So it'll put in 5 points randomly and then try and find centers for those 5 points that minimize the mean distance to all of the other points. That's more or less how k-means works. And I think there's also like k-median if you want to use that also. Now, one of the major limitations of k-means is that it really only works when data is like spherical in this way, meaning that the points are relatively distributed in a circle around each mean. And I'll show you what we do when we have like ellipsoidal distributions and stuff, and what algorithms we should use for that. Now make sure you scale your values prior to doing k-means, otherwise you'll get very skewed results. So, as you can see, this is something called a Voronoi diagram, by the way. These are kind of difficult to make, actually. They don't actually come default with like Sklearn or anything, but I have a function linked below that you'll get if you go ahead and subscribe to the Patreon and see the notes that has all of the information over here on how to create one of these diagrams. So as you can see, we've matched most of our records with the very obvious clusters. This data set's very obvious. And this is a diagram of how the k-means algorithm actually works. So as you can see, it just randomly puts in 5 different points, and then it will gradually shift the points until it can find centers that make the most sense. So you'll see, for example, this one over here, this center over here, is the one that probably changed the most in that it moved all the way from here to over here, and this moved from here to here, this one from here to here, and so on and so forth. Now you might be wondering, okay, wait, so it might take a while to actually like center these things if it picks bad points and my decision space is quite large. And you're 100% right. If you have some reason to believe that you know where the centers are, you can also initialize the points wherever you want. And we go over that in this section over here. There are a couple of ways you can initialize these centroids. So you have manual initialization, where you just give it a list of the points you want to initialize it at. And then k-means or k-means plus, which is just an improvement to the k-means algorithm that was proposed back in 2006 that picks centroids really far away from each other. I think this is the default, yeah, this is the default method used by Scikit-Learn. So let's go ahead and implement one of these algorithms and see what we can do. I'm not going to do the Voronoi diagram because they're very complicated to do, but I have an example over here in my notes on how to actually implement one of those. So you'll see Voronoi diagram. I linked the source I got the code from, and you'll see we initialize some random data, and then this is just a function you can use to create a 2D Voronoi diagram. I do wonder if someone knows how to create a 3D one. That would be really cool. But we're just working with 2D ones right now. So let's go ahead and let's go to the data and let's try doing some coding. Okay, so let me put you over here. And the data set I'm using is courtesy of Ronnie Kohavi and Barry Becker of the UCI Machine Learning Repository. For anyone that isn't aware, this is a website that just has a bunch of data sets that people can use for machine learning purposes. So, I mean, they just have tons of data sets. And they're good for just, benchmarking your machine learning algorithms or practicing if you can't find something on Kaggle. There's the link to the data set. So the first thing we're going to do is import the data. And there's a lot of data pre-processing I had to do to get this data set ready. So I'm not going to, I'm going to go over how I did that pre-processing, but I just did it before we did the video because I felt like it would just be distracting because we're past the point of like doing pre-processing with all of our, or of like learning pre-processing, my bad. So of course, go ahead and import pandas, import our data set. And as you can see, basically it's a data set. So it's like US Census data. And it's basically a data set of a bunch of attributes for different adults and whether they made greater than $50,000 in income or less than $50,000 in income, less than or equal to. And we have a couple of characteristics over here. So I'm going to go over the different pre-processing steps I decided to go through. So, data cleaning. First of all, I'm just going to remove race as a feature. This is, I don't know how YouTube will flag a video that talks about race and income, so I'm just going to, get rid of it as a feature. We're not going to worry about it. I'm also going to remove education because we have this education num feature over here. So this education num, I'm just guessing, is an encoded version of this education feature. So we'll do that. Then we'll label encode sex, meaning that we'll just assign zeros and ones to male and female. I'm not sure if that's respectively or not. Then we'll change native country to be immigrant or non-immigrant. So what happens is under native country, you can either be from the United States or you can be from, and they'll like list the countries you can be from. So they'll have like Cambodia, India, like, Hong Kong, stuff like that. So I'm just going to encode it to be immigrant and non-immigrant because if we had every single country show up, then the data set would just explode when we try and one-hot encode it. Now, if I were to actually try and predict incomes using this data over here, then I think there is some census data that correlates, where immigrants come from and like relative incomes and stuff like that. So, but again, we're just trying to demonstrate some clustering algorithms over here. Next, I'm going to drop income and store it as a separate variable because we don't need that right now. Next, I will one-hot encode working class, marital status, occupation, and relationship. So these are basically values that are variables that have more than 2 different unique values inside them. So we have to one-hot encode them. And then finally, I'll scale the values. So data import columns, just to get an idea what the columns were. The reason I did this was actually initially the data had a space in before every column name. So I was getting a key error where when I tried to like refer to a column, it would actually tell me, oh, there's no column called age. There's a column called space age, but not a column called age. So doing this was a good way to troubleshoot that error. And then I just went back into the base data and removed all the spaces. I was thinking about adding the spaces in the code and it just seemed really messy, so I just removed them in the base data. All right, so first thing, let's just drop race and education. So we're going to copy our data import. And the reason I do copies a lot of the time is because this data set's not quite large, but sometimes I have data sets that are very large, and I would like to have the computer just hold a copy of it. That way, if I mess anything up, which I always do at some point in time, then I can just re-import it if I need to. And then also, I like to be able to run every cell separately. So now I don't have to import the data again and then run this pre-processing if I change anything. I can just run this pre-processing by itself because the data import variable, that data frame will remain, whole. Next, we're going to import Scikit-Learn pre-processing, the label encoder. Of course, instantiate our class, and then drop. We'll set label encode sex, which is our new data frame, to equal drop race education. label encode sex, the column. We will fit transform that. That way we get our label encoded column. Native country, we'll copy this over here. Native country equals native country dot map lambda x. And then basically if it's the United States, it's a 0, everything else is a 1. Basically immigrant or non-immigrant. And then we're dropping the income column and making that native country. And then one hot encode data. And then this is something interesting I found out fairly recently. The Scikit-Learn method, you have to like obviously you have to remember the import, like, you know, from preprocessing, whatever it is, bring in one hot encode. You have to instantiate the class, then you have to fit transform the data, and then you get a NumPy array, which again I hate double NumPy arrays. Like it's so much harder to read than a pandas data frame. So pandas, I found out, actually just has a function called getDummies, which will one hot encode any categorical variables it sees in your data. So I just use that these days, and it is amazing. I will probably go ahead and update the chapter 2 notes, I think that's the one with the data preprocessing, to start using pd.getDummies, which is so much better than the Scikit-Learn method. Scikit-Learn is like, I hate that it uses NumPy for everything. And then let's go ahead and we bring in the standard scaler, and then let's just go scale all of our data. And then our clean data, pd.dataframe equals scale data, and then columns are, because what happens again, like I said, Scikit-Learn will output a NumPy data frame, or a 2D NumPy array, not a PD data frame. So I want to go ahead and transform it back into a data frame just for my own sanity. And that's our clean data. So here's our clean data. As you can see, we have one hot encoded all this data over here. And let's just go ahead and start clustering. So I'm going to put these notes over here. And let's see, do they fit? Oh, barely. Okay, so let's make you a little bit smaller and make you a little bit bigger. There we go. All right. I think the code was up here. And what I'm going to do probably at the end of this is I'm going to create a cheat sheet for all the different machine learning algorithms out there, only because, I mean, I've been coding for a decent amount of time right now, and like I still haven't memorized a lot of this stuff as far as like, you know, what specific class the k-means class is inside Scikit-Learn. And so I kind of came to the conclusion, oh, okay, I mean, I guess no one actually like memorizes this stuff unless they use it every single day. So like it's okay to just have a cheat sheet with all the information in it. So I'll probably create a cheat sheet with all of these machine learning algorithms and like how you implement them as a Notion page, and leave that on my Patreon for anyone that's interested. So let's go ahead and import our data. So I think clean data is the data we are looking at. Our Jupyter Notebook's glitching out, okay. Occasionally, for some reason, my Jupyter Notebooks just like glitch out, and then so I have to restart them. Luckily, yeah, the data is small enough to where it's not going to take a long time to figure out. Okay, cool, so we have our clean data, and let's go ahead and import Scikit-Learn. So from Scikit-Learn dot cluster import k-means, and then let's just say k equals 2 for now, and we'll change this in a minute. K is the number of clusters we want to find. And let's say k-means equals k-means, and then n init, I think, is the variable, is it? No, n clusters equals k-means equals k-means, and clusters. Oh, sorry, I'm just copying that line again. Let me focus a little bit. Ypred equals k-means dot fit predict, actually, because we're not transforming the data. And then we'll put in clean data over here, and we should get, so as you can tell, we have an array of every single instance, so every single row of our data, and it gave a prediction of what cluster it thinks the data is in. So that's how you implement a k-means clustering algorithm. Now, okay, this doesn't really like tell us anything. It's not, and I want to see if I can like actually see which number of clusters makes the most sense for this data. And I think I may have been a little bit confusing. We're not actually trying to predict incomes with this clustering algorithm, because that would be a classification task where we have to give it the incomes and tell it to, okay, like fit this data to that class. What we're trying to do is we're just trying to cluster our data together. And I felt like having the incomes may not be particularly, or you know what, maybe having the incomes would not be a big deal. I think for now we're totally fine, though. Let's just keep going. I probably shouldn't have dropped the incomes, though, because it's a clustering algorithm, not a classification algorithm. So now that we've done our basic classification, you might be wondering, how can we graph this data? Well, if you guys remember from chapter 8, we did PCA, principal component analysis. What we can do is we can find the two principal components and then just plot all of our data on that, because this is a multi-dimensional data set, obviously. You know, we have like 45 dimensions over here, right? So let's go ahead and find the principal components and then go ahead and plot our data on that. If I had to guess, I would guess that education number and sex probably are how, and maybe native country are probably how the data will be most separated by. But let's see what we got. So let's go ahead and implement a clustering algorithm, or a PCA algorithm, but we'll do that in 1 second. First, let's go down here and talk about a couple of things. First, if you want to increase the speed of k-means, this wasn't much of an issue. You can do something called mini batching, where basically if you have data that's too large to fit in memory, because it has to fit in memory for it to work with Scikit-Learn, you can go ahead and just like batch up the data and like put it in bit by bit. It would be difficult for me to find data that big. I have 16 gigs of memory on this laptop. I mean, which is not like, mind-blowing, but it would be, I would have to like find something that is that large. So I didn't actually implement this. But the next thing let's talk about is, how do we choose the optimal number of clusters? So we can use the elbow method, which is basically, it's kind of like we talked about earlier, where you are trying to find where you get diminishing returns with each cluster. So as you can see, this graph has K, which is the number of clusters, and inertia, which is one metric to determine how much or how well clustered your data is. There is a better metric we'll use in a second, but let's just go ahead and see if we can do this. So as you guys can tell, if I go to, I think if I do k-means over here, and then plot that inertia, yeah, it'll give the inertia of our k-means because it fit it to that data. So let's go ahead and try k-means let's go ahead and try 1 to 10 clusters and then see what we get for our inertia. So let me go ahead and create a for loop that runs that for us. So clusters. And I know you guys said you like it when I actually code on the video, so that's what we're trying to do over here. Okay, so I think I can just copy this section over here. We'll say k equals I. So for I in range, let's go 1 to 11. By doing that, it's actually going to pick values 1 through 10. And we just have an extra step over here, so let's just remove that and then set this equal to I. And then we're going to do k-mins.fit. We don't have to do the predict. Clean data. And then let's go ahead and attach our inertias. All right. So k-means dot inertia, and we actually want to append this. So we're going to create a list of the inertia values. So let's go ahead and run this over here. And then from matplotlib dot py plot import plt. Oh, wait, sorry. That's not how it goes. Come on. Import matplotlib dot py plot as Can't type today. Plot. Okay, and then let's go ahead and see what this inertias list looks like now. Damn it, I don't know why it does this. This is a bug I've been encountering recently where it runs the previous line of code for some reason. Okay, cool, so it looks like we do have some inertias that seem to go down a decent amount. So let's go ahead and plot these. So let's say it's a plot dot, and I want a scatter plot, right? Or I want a line graph, I guess. So I think that's just plot dot plot. X. Is it X? Well, let's do range 1 through 11, and then let's just make our second variable inertias and see what happens. Are you serious? Okay, so it won't run. Okay, so let me exit this, open it again, and run everything. Luckily, we don't have that much data, so it shouldn't be that hard. I'm gonna have to restart this. Okay, so it looks like there is no real... Yeah, it looks like we're not seeing any real elbow in this data. So it looks like this method won't work very well over here. Let's go ahead and try something else. So let me change this to a variable, and then I'll make this 100. That way we can easily just swap this out over here. So that might take a second to run, so we'll see what happens. In the meantime, we can talk about silhouette score. So this method is very simple, but it's like very rough as well. A more computationally intensive method is something called the silhouette score. It's the mean of the silhouette coefficient over all instances, and you can calculate the silhouette coefficient by, for an instance, by taking b minus a divided by the max of ab, where a is the mean distance to the other instances in the same cluster, and b is the mean nearest cluster distance, meaning i.e. the mean distance to the elements of the nearest cluster. And basically this coefficient will be between -1 and 1. 1 meaning that the instance is very deep inside its own cluster, and -1 meaning that the instance may have been assigned to the wrong cluster. So I'm thinking in this one what we want is we probably want the highest value for our silhouette score. So it explodes at 4 and then goes down from there. So let's go ahead and copy this as well. And we'll go run this also. So silhouette score equals cleaned data k-means.labels. Oh, okay, so we have to implement a k-means algorithm each time. Okay, so what we want to do in that case is we'll probably want to interrupt this and add it to this for loop over here. So we'll have inertias and we'll have sil scores. And that'll be its own thing. And then let's go ahead and bring this in. So let's go ahead and import silhouette score. And the silhouette score, clean data, k-means.labels. So sil score, not sil scores. So sil score equals that. And then, or you know what, no, forget about it. Let's just append it directly. Why am I creating a new variable? So let's go ahead and append the silhouette scores to this value over here. And this might take a second to run, so save that and then, oh. So something wrong with our silhouette score. Let's go ahead and change that to a 2 and see if that fixes it. Okay, so it looks like, okay, so that makes sense. A silhouette score can't work with only one cluster because B over here, I believe, is the mean nearest cluster distance. So if you only have one cluster, then that's not going to work. So, and that makes sense too. Why would I even, yeah, to be fair, why would I care about having one cluster anyway? So let's go ahead and do this. So we're doing everything from 2 to 100 clusters, and then we're going to go ahead and plot that. So we'll plot this over here, and then I want to also plot SIL scores. There we go. And that plot should show up in a second. So I'm gonna go grab some water. Oh, actually, no, never mind. Let's go ahead and go over this first while we're waiting for that to run. So we'll know when this graph reveals itself that it ran, or we can just stay over there. There's also this thing called a silhouette diagram, which I don't have the code for quite yet. It seems kind of complicated to put together. But basically, it's every silhouette coefficient sorted by the cluster it's a part of, and the height represents the number of instances in that cluster, and the width is the sorted silhouette coefficients of instances in the cluster. Wider is better. The dashed line is the silhouette score, and you want most of your clusters to fall to the right of this line. So for example, in k equals 3, that's not the case. In k equals 4, it's kind of hard to tell, but this yellow one is past that red line. And so that's why we would want that. But it's what it's saying is that 5 clusters actually makes a little bit more sense because the heights are more even, which is better for our data. So this is where the silhouette score actually disagrees with the elbow method we had over here, where we were like, oh, 4 is clearly what we want, but 5 is actually what this diagram says we should be using. So one thing that I mentioned earlier is that k-means is not a great solution when clusters have varying sizes or different densities, or non-spherical shapes. As you can see, these are ellipsoidal. And this is where you'll see k-means doesn't work very well. Now there's a section over here where they go over clustering for image segmentation. I'm not going to spend too much time on this because you're better off using neural networks to like process images anyways. And I have some notes on convolutional neural networks and stuff like that if you guys are interested in seeing those. But basically, here's the code for what they're running. So what they did is that they took an original image and then they're using just the color as the dimension that they are clustering on. And so by reducing the number of colors, you can simplify the image. And you might notice, wait a second, red is obviously a very different color. Why is that going away very quickly? Like if you were to ask me, what are the 3 main colors in this image? I would say green, yellow, red. So why is under 4 colors red basically gone and grouped with green? Well, this illustrates I guess you could say problem with k-means, where k-means expects that you have clusters of relatively similar size. And in this case, obviously, the red occupies a very small space in this image, which is why it is not, it is taken away actually by 6 colors really, and merged with brown, it looks like, instead. So that's why you, in this instance, this is one of this is one way to illustrate one of the limitations of k-means clustering. So basically all he did is he just like brought in the image. So we imported the image, turned the colors into a NumPy array, and then just went ahead and imported that. So let me expand it this way so that it's a little bit easier to read. And here's the code for that section over there. So pause the video if you want to take a look at that. It kind of just seemed like the reason I'm not going over it is because it doesn't seem like practical use of this method, because if I ever need to do any like image classification or anything, I usually use neural networks because they're significantly better at this stuff. This one was interesting, using clustering for pre-processing. So clustering can be an efficient technique for dimensionality reduction. That's kind of like what PCA was, if you guys remember earlier. And we're going to be doing a PCA in a minute after this decides to run. And what happens, you can look at like this MNIST like data set is basically MNIST again, but with numbers instead. And what it does over here is it's using k-means to reduce the number of dimensions of data that the machine learning algorithm has to look at. So what we're doing over here is by creating clusters of data and simplifying our data into a bunch of cluster centers, the machine learning algorithm that you implement next can work significantly faster. It doesn't make much sense on this data set. You'd have to have a massive data set for this to make a lot of sense. But this actually is one instance of how we can actually speed up our machine learning training processes. And PCA is another really popular use of a unsupervised machine learning algorithm to actually reduce dimensions. And then semi-supervised learning is kind of what they were talking about at the beginning of the chapter when they talked about how the majority of data in the world is unlabeled. And what semi-supervised learning is basically if you have some labeled data and a bunch of unlabeled data, but you need more labeled data, you can use the labeled data and a clustering algorithm in order to label the rest of the data. So you'll see over here, what they're doing in the, and this is just the example from the book. Basically, we bring in all of the numbers and we remove the y value. We have the y value, but we remove it. And then using the clustering algorithm, we're able to actually label the data with a very high degree of accuracy. So what this does is this basically gives us a significantly larger amount of labeled data, which we can then put into another machine learning algorithm to predict whatever we want to predict, or train that machine learning algorithm. So this is a great way to give yourself more data if you don't have enough data. Oh, and then let me expand this so you can see the code over here. As you can see, this section would take quite a while to go through. Chapter 9 is a long chapter, and I should note, I don't know how many people are watching these videos in lieu of actually reading the book. I'm of the opinion that you should read the book, and these videos are kind of like a summary of each chapter. Someone in the last video made a really good point where I missed out on a section of the chapter, and I skip over some sections that I don't think are as important. I'm sure in school you all noticed that teachers never went through the entire textbook. They just went through, a couple of sections here and there, which made the most sense for them to go over. And I'm kind of doing that same thing, where if I don't see something that makes much sense to spend a lot of time with, I kind of just gloss over it. But that's why I think it's best that everyone reads the entire chapter themselves. Next we have dbScan, which is a very different way of handling clustering from k-means. And what it does basically is that for every instance, the algorithm counts how many instances are a distance called epsilon away from the cluster. And this is called the epsilon neighborhood. So not the E minus neighborhood, it's the epsilon neighborhood. And if instances have at least, you know what? I don't know how long this will take. Let us interrupt this, and let's just do 1 through 20, and run that, because I do want to actually do some PCA on this as well, but I don't want to wait forever for this to finish. What I'm guessing is that means that we haven't really hit the elbow quite yet. That could be what it means. Because it is reducing quite rapidly, it looks like. Hopefully, it should be able to run 20 clusters relatively quickly. I wonder if I have... Oh, you know what? No, you know what I should do? Okay. I need some way to track what cluster we're even at. So TQDM would be a better library for this, but I have a bunch of issues installing TQDM for some reason, so I'm just excluding that for now. Actually, just 2 clusters takes a while, looks like. All right. So, sorry, back to dbScan. So if an instance has at least a minimum samples instances in it, then it's in its neighborhood, including itself, then it's called a core instance. Basically, core instances are those that are in densely packed neighborhoods. And multiple core instances can be strung together close enough to create one single cluster. And any instance that is not a core instance and doesn't have one in its neighborhood is called an anomaly. So it's quite different from a k-means algorithm. So we will implement this in a second. It looks like we're making some progress through this. So I'm going to go grab some water, and I'll be right back. And then let's go ahead and hopefully this will be done by then. Oh, shoot. Okay, cool. We're done. All right, so we got that. Okay, and then let's plot this. So it looks like it's still just going down. Okay, so I probably have to do more clusters than that. Okay, look at our silhouette score. This is interesting. Interesting, okay. So I think I'm going to pick a cluster size of 11. 11 sounds like a good cluster size. We'll go with that. So let us, and yeah, let's just go with 11. Who knows how much longer this can go for. So let me copy this code over here. And then we'll go down here. And then the cluster size, we'll make it 11. Run that. Oh, I didn't mean to do that. Oh well, that's fine. And we will get our clusters. right, awesome. So now what I'm going to do is, in order to actually visualize these clusters, I'm going to use PCA to reduce the number of components down to just 2. So let me go ahead and pull PCA. If you guys remember, PCA stands for Principal Component Analysis, and is a way that we can find we can basically transform our data in such a way. It's kind of like twisting the entire way we look at the data in such a way that we are looking at the most important parts of our data correctly. So clean data, X2D. All right, so here are our principal components. Let's call this first one X and this second one Y. So what I need to do is I need to plot this. So plot dot, I think it's just scatter. And can I just put in X2D? That would be nice if I could. Anyway, I couldn't do that. That would be too simple. Okay, so let's say for point in X2D, and we'll have something called X points, which is a list, and then we'll have something called Y points, which is another list. So for point in X2D, X points dot append point, and then we'll append the first value, and then Y points will be the same, but it'll be the second value in that list. Okay, and then I should be able to put in X points and Y points here. Huh? What happened? Oh, frickin'. I can't run this code again because it takes too long. Yeah, I don't know why. Okay. There we go. Ah, interesting. Okay. So it looks like we have like 3 obvious clusters over here. And again, this is the thing I love about PCA. This is completely like, random data. And we already are getting some insights over there where it's obvious that there are like 3 major clusters. I would argue there might even be like 7 major clusters. There's like 1 over here, 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 and 1 over here. I wonder if I can just assign colors by putting in Y pred. I probably can't. Okay. Oh wait, plot scatter. Okay, let's see. Add color to matplotlib plot. For YC in zip ys equals... Oh, okay, it's just an exponential function. You know what? Let's try this. Instead of doing it this way, let's just do it the dummy way. PD.data frame. And then let's go ahead and put in data equals x2d. And then columns equals All right. Interesting, okay. How do you just stick... No, yes, pd.concat, if you just want to stick to... Yeah, let me do it that way. I just want to do pd.concat. Oh, right, I forgot. I need to do it like this. So pd.concat, and then I need to pass in a list of these things. There we go. And then I need to set the axis to something. There we go. And then we'll just do .to_CSV. And we'll call it clustering.csv. Index equals false. I almost never want the index. Awesome. Okay, so now what we'll do is we'll go ahead and import or input Tableau. Or sorry, we'll open Tableau and input this in Tableau. It'll take a second to launch. All right, so we have our data over here, X, Y, and then let's put cluster over here, and then put that under colors. Okay, interesting. Oh, and it didn't plot every value. Okay. Oh wow, actually no, I would have benefited from having an index here because I can add an index to the detail column or detail box, and so let's go ahead and just re-export that. And then we will refresh this. And you'll see F1 is now there, and that we'll call that a measure, add it to detail. There we go. Interesting, okay. So cluster 0, interesting. So cluster 0, these are all together for some reason. And as you guys can tell, these are like individual instances. So we've done a couple of things over here. We've, first of all, done our PCA to come down to just 2 principal components. You could also do 3. The thing is, I don't think Tableau actually handles 3D plots, which is a bit weird if you think about it. Like, it seems to me like it should. But, okay, whatever. And it seems that the clustering algorithm is not doing the best job in actually getting us our cluster lengths. And maybe it has to do something with the fact that these are ellipsoidal shapes. Remember that k-means works best when you have circular shapes. So it looks like we tried to implement something and it didn't really work out too well, but went through the whole process of actually doing it. All right, so let us go to the next section. dbScan, they didn't have much code on this section. Basically, you implement it similarly to how you implement k-means. And Gaussian mixture models was very interesting. So there's this video over here which explains it way better than I could ever explain it. There's a link to the video. But basically what you're doing over here is, one, Gaussian mixture models are great if you have ellipsoidal data sources, so, or ellipsoidal points, so points that are like kind of like an oval shape. And what we're trying to do over here is basically the process of fitting this is you determine what the center of mass is, you determine what the covariance is, and, or sorry, let me back it up for a second. So there's a couple of ways to look at it. One is you're trying to find the kind of like hump over here that will raise these points the highest. I didn't really understand it, but that's the like verbiage that they used. So what happens is you start off with some random Gaussians. A Gaussian distribution is basically like a normal distribution, right? So you start off with some random Gaussian distributions, and then color points according to the Gaussian. So basically, if we had, you can see they plotted a Gaussian distribution over here and a Gaussian distribution over here, and you plot the points in proportion to how close they are to each type of distribution, to each distribution. So as you can see, these are like brown or, gold, I don't know, gold and blue, and these are just blue and these are just gold. Then you move the GMMs to be close, or you move the Gaussian distributions to be closer to their individual, like you replot them where the blue points are surrounded by their own Gaussian and the yellow gold points are surrounded by their own Gaussian. And then you keep doing that until you have diminishing returns, basically until your model converges. So when you have a GMM, you use mu to represent the mean or the center of the Gaussian distribution, and sigma to represent the size, shape, and orientation of that model. So the mean is the center, and the size, shape, and orientation is the sigma. This over here, size, shape, and orientation. And then you have phi to represent relative weights of these different points over here. And then you can get each of these variables by using these attributes over here. So gm.weights, means, covariances, etc. And then you can use it to predict a new instance, what class it'll be a part of. Because a GMM model is what they call a generative model. You can actually put in new samples and then tell it, okay, what cluster is this going to be in? Or sorry, let me rephrase it. Sorry, you can sample a couple of values and see, okay, like what was this going to be a part of? And then you can get the density of the model at any given location. Again, without actually having to implement this, I'm not really sure. Like, this part was very confusing for me. Now, there's a couple of, convergence can be a little bit difficult with GMMs, and that's where you want to use the hyperparameter covariance type to pick between spherical diagonal or tied shape for the ellipsoid. So spherical means that your clusters are all spherical in shape. They have to be spherical in shape, so it only looks for that. Diagonal means that all clusters need to be ellipsoidal in shape. Tied means that clusters have the same ellipsoidal shape, size, and orientation. So they have to have the same covariance matrix. And then the default parameter says that cluster can take on any size, shape, or orientation. This is what it's set to by default. And you can use GMMs to detect anomalies, and by detecting any instance that lies in what's called a low density region. So in this case, a low density region would be somewhere like over here. This is a low density region. You're not near any GMMs. And then novelty detection is the same thing, but coming from the opposite angle, where anomaly detection is you don't necessarily assume that your that your data is full and correct. Novelty detection, you assume that, and you're just looking for novel values. To set the number of clusters, you need more statistically rigorous methods with GMMs. And what you're trying to do is you're trying to reduce the theoretical information criterion using either the Bayesian information criterion or the Akaike information criterion. How to pronounce Akaike. Let's see.
We are looking at how to pronounce this Japanese name, as well as how to say more interesting, related, and very often mispronounced names.
Bro, just tell me.
Especially from the world of mathematics. This was the name, Akaike.
Akaike. Okay, cool. Akaike, that's all I need. I needed that 1 second of audio. So Akaike, information criterion. So AIC and BIC tend to pick the same model, and they prioritize models that have fewer parameters inside them. So basically simpler models. And you can see when we plot the number of clusters, versus the information criterion, we have our values over here. And then Bayesian Gaussian mixture models, if you provide a number of clusters that's greater, so what happens if you provide a number of clusters that's greater than the number of clusters you expect to be necessary, the Bayesian Gaussian mixture model will give you weights close to 0 for any unnecessary cluster. So this is another way you can use to determine how many clusters you should actually have. So as you can see, we go down the array, and it looks like this model only needs 3 clusters. And there's a couple of other algorithms for anomaly and novelty detection that they, just describe in the book. It's in the last 1 or 2 pages of that chapter that you can go ahead and look at. And I have some extra content on actually other clustering algorithms that you can use with Python under the Machine Learning Mastery webpage. But thank you guys so much for joining. I'll just do a quick run through of this notes page. That way, in case you don't want to subscribe to the Patreon, you can, you have all the notes over here. You can take screenshots of this. But again, it's a great way to support the work I do. As I mentioned before, this is probably the last chapter I'm going to do for a little while because I personally don't need... So this was a learning journey for me, and I personally don't feel like I need to go over neural networks right now. What I really need is a stronger grasp of statistics, and so I'm probably going to start learning something to do with statistical learning next. I'm not exactly sure what I'm going to do, but we'll see. I will consider this kind of the end of this series, at least for the near future. But thank you guys so much for joining today. If you have any questions, leave them in the comment section below. I know this video is a little bit less, I hope it's as informative as the previous ones. I feel like I didn't understand this chapter as well, but I did want to come out with the video at some point in time. I can see myself in the future, I can see myself in the future coming back and doing these videos again. When I am a more seasoned data professional, especially with data science and stuff, because I'm a data analyst. But when I am a proper data scientist, I can see myself coming back and doing this series again and explaining these videos more clearly. Also, speaking of people who are very seasoned data scientists, there is a tremendous, here it is. There's a tremendous series that Bloomberg has, which is called, it's part of a playlist. I think you can go over here to Inside Bloomberg, and then go to Playlists, and then it should be a playlist. Okay, it's not. But basically, look for these videos over here. Basically, they are a series of machine learning videos that offer graduate level information on machine learning. It's really, really cool, and they're really well done. The guy that presents them, this dude over here, is hella smart, so these are great videos. Thank you guys so much for your time, and if you have any questions or concerns, leave them in the comment section below. Please remember to like, comment, and subscribe on this video. Even if you have a comment just saying hi, that's a great way to show the YouTube algorithm that you are engaged with the content I'm creating, and we can spread this content to more people as necessary. But thank you guys so much for your time, and I hope you have a good day.